I'm very happy that we have Ulrich to present us today some work on the Little Endian for the powerpc. Last year, Ulrich did present some things on the powerpc in Paris, and this was really very interesting because of his past experience as a GCC developer. And I'm really excited to hear about his Little Endian experience. For my personal case, I've seen that in complex systems, Indianness with heterogeneous systems can be a real pain.
Thank you very much for the introduction. My name is Uli Weigand. I'm with the IBM Linux Technology Center, working on compilers and toolchain. And as was just mentioned, I had the opportunity to present in last year's conference in Paris about what we are doing now in IBM with LLVM, where I said, okay, we have made the decision that we want to make sure that LLVM does support the IBM platforms, which is PowerPC and System Z, the mainframe, well. And basically, the short of this talk is to give an update on that. We managed to do that, so Power and System Z are now supported. And so to keep things from being boring, we decided, okay, now let's do a new platform, which LLVM again doesn't support, so we still have work to do. So I'll be talking about Little Endian PowerPC. First of all, a little bit, well, what's this beast? Why would anybody want to do Little Endian on a PowerPC? And then once we discuss the platform, I'll go to discuss the ABI. Why would we want to define a new ABI for the platform? What is the goals? What do we want to achieve? And how did we go about doing that? And then sort of the meaty part of the talk is then actually going a little bit about the details of some aspects of the new ABI to give you some feeling sort of what the problems are, in specific examples showing code. And finally, I'll be talking about, well, how to go about implementing that in LLVM. First of all, well, implementing it generically across all the aspects of the open source Linux ecosystem, and then, of course, in particular, implementation LLVM. Why isn't it implemented yet? What problems have I run into? What needs to be done to get this fixed? But first of all, just as a remark, I didn't come up with the new ABI all on my own. It was a whole team across many of the areas involving power inside IBM. Of course, a lot of the LTC folks that have been doing power toolchain for a long time, but also beyond the LTC, we've been working with some of the power architecture people. We've been working with some of the IBM proprietary compiler people, like the Excel people, the IBM Java people. So you get a list that's long like that. Okay, Little Endian PowerPC 64. As most of you will probably know, PowerPC, well, most of you who have been working with PowerPC will probably think of, well, PowerPC is obviously big endian. But actually, if you look at the hardware specification, the architecture, the ISA, that has never been quite true because the hardware actually has always, at least for a very long time, supported both endianness. So you have actually a bit that you can flip somewhere that tells the hardware, okay, should I do little endian data accesses or should I do big endian data accesses? And in fact, I'm not really familiar with that area, but I understand that in some use cases where 32-bit PowerPCs have been used in embedded systems, some people have actually been using that little endian mode in the past. But it really has never been used in the 64-bit, in particular in 64-bit server space. All the 64-bit server operating systems, both the IBM AIX and Linux and all the other operating systems has always been only 64-bit only. And there's some reasons for that. There's been some issues with the hardware. While the architecture supports Little Endian, the actual microarchitecture implementation didn't give you the same performance. So in the current power systems, if you switch to Little Endian mode, it will work according to the architecture, but you won't get the same performance you get if you run in big endian mode. And I mean, that was one of the reasons. I mean, nobody was using it, and therefore the hardware wasn't tuned so good. And because the hardware wasn't tuned, nobody was using it, right? But that is going to change. So what is changing? As I mentioned, the hardware. So there is a new iteration of the power processor that will be coming up and it will be announced. So it has not been announced yet, so I can't go into much detail. but people know that Power 8 is coming. There's been code contributed to GCC and LLVM already. And it will support LE with the same performance as Big Endian. So that's one of the obstacles going away. And that's also something that has been going on. And if you have been watching sort of what's been going on in the distribution space, whether you look at Fedora, or OpenSUSE, or Debian, or whatnot, you will have seen that there is something Power Little Endian that people have been working on to actually build Linux distributions for that platform. That still doesn't quite explain, well, why are we doing that? And this really all ties back into another effort that has been announced a while ago, a couple of months ago, which is the so-called Open Power Foundation, which now, since I think 1 or 2 weeks, actually has a website, so you can go to openpowerfoundation.org to have a look at what this is all about and what they are doing. Basically, the idea is to sort of expand the reach of Power, the Power architecture, into new areas where Power hasn't been really used before, by opening up some of the ecosystem, by allowing people that are not IBM to build systems around Power, using Power processors, using Power cores as part of larger systems. And in the context, I mean, that's to a large extent, it's a hardware and licensing and firmware issue, but there's obviously software issues associated with it, and so software is also part of that foundation. And one request that we were getting as part of, in that context, was that people were saying, okay, well, now we want to build our system with Power Core and some other stuff around it, but we are running into problems with the endianness, because either we have other hardware around that really would like things to be Little Endian, or we have an extensive software stack or extensive set of binary data that we already have and we need to continue to use, which is in Little Endian format. So it's going to be difficult for us to use Power, right? And well, when you get enough customers and big enough customers that tell you things like that, at some point change happens. So we thought the decision was made, okay, well, Power hardware actually supports it, so it's just a matter of getting the software right. Just a matter of some small amount of work. So, Little Endian Linux. There will be a new Linux platform already there, PowerPC 64 LE, IBM Linux. Right now, we are planning, this is it, so you will get 64 with Little Endian. There will be no attempt to try and support any sort of coexistence with Big and Little Endian on the same system. And there also will be no effort to try and get a 32-bit, either Little or Big Endian environment, so it will be 64-bit Little Endian only. I mean, it's 2014 now, and hopefully by now everybody is happy with 64-bit. And also because of those hardware issues that I mentioned and alluded to earlier, it will really only be supported on Power 8 and up. So right now you cannot, I mean, Power 8 is not out, so right now you cannot actually get a system, unless you're special friends of ours. But there's emulators, QEMU supports it, and so you could actually play with it in an emulator right now. Also, I mentioned Linux distributions. Again, if you see sort of in the community space what the community distributions are doing, you will notice that there is effort around getting a Little Endian distro up and running. And you can see that, you can download that, you can go to OpenSUSE or Debian or Fedora or whatnot, and actually download quite a lot of packages already. But sort of the official statement that we now support this platform has not been made by any of those distros, and it, of course, as always, it's up to the distros to actually make that statement, and we'll see what exactly is going to happen in that space. Now, technically, what's the big deal? What's different? Well, obviously, the byte order is Little Endian. What else? And that's where we come to the meat of this talk. We also decided to do a new ABI. And that's not because we had to. I mean, you could have just used exactly the same stuff as right now and just did everything Little Endian. Would have worked. But the point is, when you do everything Little Endian, you are completely 100% incompatible to existing applications anyway. So there's no question of compatibility. It's just not going to work. So if you have that sort of clean break, you can change the ABI, which is something that you very rarely have the opportunity to. And so we thought, okay, let's take the opportunity. Let's look at the past experience we had with Power ABI. Let's see if there isn't something we have always wanted to fix but couldn't because we couldn't break compatibility. And that's what this is about. The PowerPC ABI, the 64-bit, really goes back, I mean, in sort of its concepts to over 25 years ago. This was the Linux ABI is based on the AX ABI, the AX 64-bit ABI is based on the AX 32-bit ABI. So there was never sort of a point where we really made significant changes. And a lot of the decisions that went into the design of the ABI back 25 years ago may no longer hold completely true today. I mean, the hardware has changed, the hardware microarchitecture, what's fast, what's not so fast on the chip has changed. And the use patterns, like people don't use so much Fortran anymore, they use other stuff, which shows different patterns on how many function calls you have, how large your functions are, what data accesses you tend to do, and so forth. And so over time, when doing performance measurements on current Linux systems, from time to time, the performance teams have run into things like where we said, okay, well, that's stupid. Why are we doing that? Oh, because the ABI says we have to do it that way, right? And we couldn't change it. On other platforms, there have been changes more recently. I mean, Intel, when they introduced or AMD, when they introduced the 64-bit platform, they did a new ABI. ARM has just now done 64-bit, and they did a new ABI there. We didn't have the chance because we didn't do it back when we introduced 64-bit. So we thought, okay, now we have the opportunity. Let's see and have a look what we can do. So obviously, we did not want to throw everything away that we had so far and start from scratch completely because, I mean, the chip is still a PowerPC, and a lot of things, the problems that you have in PowerPC are still the same. And of course, the existing ABI has been established, is being used, has been used for 25 years, and so we didn't want to throw anything away that we didn't have to. But at the same time, we wanted to look into what do we have. Are there things where we think we should change something to achieve a number of goals? And and there's really those three that I have here. So the one is we wanted to make things align with the ecosystem that is most widespread, that has seen the most widespread use, which is really Intel, or I guess ARM to an extent. But really the point is we wanted to avoid things that when you have code that runs elsewhere and you want to port it to Power, that gives you trouble, right? And there are some things that are just unavoidable because they're part of the hardware. But if there's some artifacts that are part of the ABI, we said, okay, let's see if we can get rid of them to make things just work and look the same as elsewhere. Second is we wanted to make sure the ABI would allow us to exploit hardware patterns, hardware capabilities that have come into the recent Power hardware generations and that we may be expecting from future hardware generations, right? And the third one is to make sure that the ABI is really good for modern code patterns, which is object-oriented languages with classes, with the abstraction that goes with it, with the typically shorter functions, more calls, in particular more indirect calls, and so forth. So, how did we go about designing the new ABI? We didn't want to do it just on paper, we wanted to have real hard facts. So what we did is we actually went for a real prototype approach, where we said, first of all, we want to implement the new ABI on our existing hardware, which at the time was big endian hardware because we didn't have little endian hardware, we didn't have little endian operating systems, so we just had big endian. So we said, let's do the ABI on big endian. And so basically what we have now is we have this orthogonal approach where we can have the old ABI or the new ABI, and we can have little endian or big endian. Any combination is technically perfectly feasible. It's just that sort of, we're not building a full distro for each of those four. We're just building, I mean, we obviously have the distros for the old ABI on big endian, and we will be building distros for the new ABI on little endian, but for testing purposes, you can do any combination. And that allowed us to test basically every change that we were considering for the new ABI on real hardware using a real full implementation of the core toolchain, Binutils, GCC, glibc, building a library, building the benchmarks that we were interested in, and just running it in for real on real hardware. So now, what did we come up with? This is sort of the core things that we did decide to change. The first is, if you've ever seen PowerPC 64 ABI, you may have wondered about what's this whole thing, or this weird thing about the function descriptors. Well, with the new ABI, we don't have function descriptors anymore. A little bit more about that. The second point is pretty much just a me too. So on other platforms, we have position-dependent code versus position-independent code. So you can build shared libraries that are relocatable, or you can build your main application that's not relocatable and be a little bit more efficient. On Power, we never had that for various reasons. Everything was Power position-independent. And now we say, okay, well, we can do the same as everybody else and have main position-dependent, make it a little bit more efficient. And some optimizations to parameter passing with structures and registers, and slimming down the minimum size of the stack frame. And I'll have more on that in a couple of slides as well. In addition to these major changes, there was a number of changes where we said, okay, these were already options because they could be implemented in a compatible way in the old ABI, and we just said, okay, in the new ABI, let's just start out right with sort of requiring that and making it the standard. Which is some optimizations for where to save the talk point and so forth using the medium code model. I'm not going into much detail about that because that's not really news that we had that already before. Okay, now I mentioned the two areas I wanted to look at a little bit in more detail. One is what's called talk addressability, which is all about function descriptors. A little bit of background, when you use talk sounds weird. Maybe you're more familiar with the term GOT, which is used on Intel. It's exactly the same. It's just Power. We have to call everything by a different name. But it is exactly the same thing. So the idea is if you have code that is position independent, that is loaded at runtime at different addresses, your data can be at different addresses too. So you need to find your data. And one way to do that is to have a sort of directory. In particular, if you have multiple shared libraries that are all loaded at different areas and you want to access data in one shared library from a different shared library and stuff like that, you need to know where the data is. And so the talk is pretty much a dictionary that tells you where and what addresses all of these data elements that you want to access and code elements have ended up with. Great, you have this dictionary which tells you all the things, but where is my dictionary, right? So I need a starting point, and that starting point is the GOT pointer or talk pointer, which is pretty much just a pointer to that dictionary. And this pointer is in a register because we have to start from somewhere. But, well, how does the value get into that register, right? Somebody has to load it. And it can't be loaded just once at the start of the program, because if you have multiple shared libraries, they will have different, each of them will have their own data dictionary, their own talk. And so when you do a call to a function, a different module, somebody has to load the new value, the appropriate value for that shared library. And when you return, you have to restore the old value that you used for your own shared library. And of course, well, function calls, there's different ways. You can have direct calls and indirect calls. Direct calls go to a function symbol, and there's various things that can happen. Can be in the same module, which is easy. It can go to a different module, to a different shared library, where you don't know where it is because you don't know the address. So what will happen is the linker will insert a little stub that directs your call to the stub, and the stub will load the final address from your data dictionary, from the talk, and branch to it. And the correct value in the talk will be inserted by the dynamic loader that actually sets up your whole address space when you start executing the program at runtime. And an indirect call obviously always has a variable that holds your address in some way or form, which is used for C function pointers, C++ virtual functions, and all that kind of stuff. So for indirect calls, you never know whether it's going to go to the same module or to the different module, right? So these are the cases to consider. And each of those cases you have to consider, do I need to load my new talk value? Who does it? And how do I do it most efficiently? And this problem is pretty much a problem that everybody has, and people have been solving it in different ways. The most basic distinction is, does the caller have to set up the talk for the function it calls, or is the callee able to determine the value for itself? And the decision that we made, or that folks made back when they defined the PowerPC API, the old one, is that it would be most efficient on PowerPC for the caller to provide that value to its callee. Now, if the caller and the callee are in the same shared library, that's trivial because they use the same talk, so there's nothing to do. But if it's a different shared library, it gets complicated because the caller doesn't really know what talk the callee needs. And therefore, for every function, you basically have to have a small block of data on the side that tells you, when I call this function, where is the function and where is its talk. And this little block of data is what we call a function descriptor. And a function pointer on PowerPC does not point to the function code, it points to the descriptor. And the descriptor points to the code and the talk, which is a little bit confusing and different and makes some of the tools that operate on binary files just not work unless you fix them for power. On other platforms, it's usually the callee that determines its own talk. The problem is here that usually you can't just load it as an absolute value because it's position dependent, so it will move. But what you do is you want to find out where your own code is and then set up your talk relative to your own address. And that's trivial if your processor has a PC relative instruction because it can just load an address relative to your own position, which is what Intel has, Intel 64-bit has. When you don't have that, like what they did in Intel 32-bit and also in Power 32-bit, the Linux API is, you can sort of do an artificial function call because a function call will set up a return address, which is where you came from. So you do a function call to the next address and just read out the return address, which works that, as you can imagine, in particular on modern CPUs that try to optimize function call return stacks and stuff like that, it's not very efficient, which is why nobody is doing it that way anymore. And sort of the intermediate solution is that you can have the code address provided by the caller to the callee, which is easier than having the caller provide a talk because the code address is something that the caller will usually know anyway because it is calling that code, right? In particular, if you have an indirect call. If you use a direct call, it gets tricky, which is why the platforms that did it before, Alpha and MIPS, pretty much prevented direct calls. So they would always use indirect calls, which is also a little bit inefficient. So what we have chosen to do for PowerPC is we sort of try to get the best of all worlds and said, we have a function and you can choose how you want to call it. You can either call what they call the local entry point, if you know the talk, which is if you call from the same shared library. You just call the local entry point and you're done because the talk is already set up. Or if you call from a different module, you call the global entry point, and the global entry point needs to be provided with its own address in a different register. And so you can either call the global entry point, which will use that address to set up the talk just by delta, or you call the local entry point. And you can do an indirect call to the global or a direct call to the local entry point. And when you work out how it all works with PLT calls and direct calls versus indirect calls, that all works out rather nicely. You pretty much know where you have extra instructions, so it all works out fine. Now, I said we wanted to avoid weird stuff. Isn't that just more weird stuff? Well, in a way, but it's less weird than we had before, because on the ELF side, there's still just a single symbol, which points to the global entry point. So if you have a tool that doesn't know anything about that and just looks at the function, it will just see the function from start to end and be fine with it. And the local entry point is encoded into special extra information that's part of what they call the ST other bits in the ELF symbol table, where there's room for platform-specific bits. And we used those to say, okay, this has a local entry point that is 8 byte or however many bytes of the global entry point. Leads to normal function descriptors, is as fast as we had before, a little bit faster even, depending on what you measure. There's a number of more additional optimization opportunities that I'm not going into detail right now. You do have to have some cases that do need to care about the dual entry points, but we found that were relatively few cases, and in most cases it just works transparently. Now I'm doing pretty bad on time, I see. Let's just go quickly over the second area I wanted to talk about, which is passing parameters. So passing parameters is about really making sure that when you call a function and pass parameters, put them where they will be needed anyway. So if you pass an integer, pass an integer register. If you pass a float, pass it in a floating point register. If you pass a vector, pass it in a vector register. Now for scalar parameters, this is done anyway. But with object-oriented languages, in many cases we have stuff wrapped into structures or classes. Now, if we have a class that has just a single element, which is a float, it's already also passed in a floating point register. But if we have more than one, if you have 2 floats or 3 floats, which is pretty common practice if you have complex or a three-dimensional coordinate structure, something like that, you really want to pass those in floating point registers too. And other platforms do that already, so we basically just looked at what ARM did and said, okay, we want to do the same on Power. So basically, if we have a class that has just floats or just vectors up to 8, we will pass them in the appropriate sequence of floating or vector registers. And everything else is still passed as it used to be before. We also fixed some of the function return values. Similarly, again, sort of the idea being, well, the way you pass the argument is also the way you should return it, so that a trivial function gets can be trivial. So these homogeneous float and vector aggregates we also return now in float or vector registers, and also we return small structures of up to I think that number is wrong. It should be 16 bytes here. Up to 16 bytes we're passing in GPRs as well. And only larger non-homogeneous structures will be passed by reference in memory. That's all pretty much, I mean, these are the kind of trade-offs that people have been doing in other ABIs all the time. What's a little bit more tricky is the way we handle variadic arguments. If you have a function that has an ellipsis, which means like printf, where you can pass different types of parameters depending on the caller. Because there's a trade-off between making your regular function call use all the registers you have and making your variable argument handling be able to stuff all the parameters into a parameter list. Like if you do a VA start, you have to set up a VA list that holds all the information you need to find all the arguments. So if I pass arguments in floating point and vector and general purpose registers, all these have to be collected somewhere and put into this VA list. Otherwise, you can't get the values out of there anymore. But you don't want to save all vector registers always, just in case you might have a vector argument when you basically never have. I mean, in 99% of cases calling printf, you don't have vector arguments, right? So it used to be all very simple back in Intel 32-bit, where all parameters were being passed in memory anyway. So your VA list would just point to that place on the stack where the arguments are, and VA arg would just increment that pointer. All very simple and trivial. But we don't want to do that because we do want to use registers now, okay? So what other platforms did, like Intel 64 and through 90 and others, is, okay, we use all these registers, and if we do a VA start, we save all registers somewhere, put up a data structure that tells us where all these things are, and then have VA arg operate on the data structure and have 2 or 3 or whatever different counters and get all the stuff from the right places, which works, but gives you pretty tedious code for the VA list. So the power had sort of an intermediate way, where they said, well, we pass stuff in registers and memory, but we leave enough space on the stack that you can reconstruct a linear in-memory list by just storing the registers into those free spaces that we left on the stack. So if you do a VA start, it will just store registers, and then my VA list, again, is just a simple pointer. But that works only if you use GPRs. It doesn't really work if you use FPRs or VRs. So we have to sort of decide when calling a variable argument list, we want to put parameters just in GPRs and not in FPRs or VRs. But sometimes we don't know whether the function we're calling is variable argument or not because we don't have a prototype. So in this case, we just load it into both places. And it still works. A little bit inefficient, but it works. And this was all nice, and we thought about changing that and doing it more like Intel, but in the end, we came to the conclusion, okay, well, it works well enough as is, and there's no big need to change it, except for one piece, and that is, we always need to reserve the space on the stack, right? Even if even if it definitely cannot be used for anything, because we know the function is not variable arguments, it doesn't have anything else on the stack, but we still have to reserve this rather big chunk on the stack just in case it could be needed. Because one of the goals was we wanted to try to reduce the stack space consumption for things like kernel stack and stuff like that. We said, okay, in this case, when we know for sure it's non-varrock and has no other things on the stack, then we actually say, okay, in this case, we don't need to reserve any additional stack space. As I mentioned, that last point was really to help constrained environments like Linux kernel, hypervisor, framework code, every place where we have really limitations on the size of the stack. So that's why we avoid this register safe area. And there's also some other fields that we could eliminate, which overall had the effect that to reduce the minimum stack frame size of a function that just calls another function can now be done in 32 bytes, where it used to be 112 bytes in the old ABI, which is quite a significant improvement here. Okay, that was the details. Implementation. It's fully implemented in the core toolchain, which is Binatal, GCC, glibc, GDB. We fixed a number of other packages that have their own stuff like libffi, and a number of packages implement the ABI. There's still a small number of packages where still a lot more work is to be done, and that includes, of course, LLVM, but includes things like Valgrind and Mono, and we are working on these. But nevertheless, that these couple of packages don't work yet with the things that we have so far. I mentioned distributions have been started porting, and we pretty much can build 95, 97% or whatever you have of the packages in any of your regular distro. So literally tens of thousands of packages have been built with the new ABI and are to a large extent available already for download on the usual distro sites. Now, what about LLVM? Why doesn't LLVM work yet? I'm working on it. I have implemented all the function descriptor, talk, function call stuff. That's all done and works. I have not yet posted it, but I should be fine enough to do that really soon in the next couple of days or next week or so. The one thing I've not yet implemented is the homogeneous struct change, and I'll have a little bit to say about why, or sort of the issues I ran into that. It should have been simple, but it turns out that there's some issues. And those are in part because the code needs to be refactored so that we can support both the old ABI for big endian and the new ABI for little endian, and we already have to support the Darwin ABI and the 32-bit ABI. So it's just, but that's just usual software engineering, try to make things clean. But there's a second split between parts of the ABI implemented in Clang in the front end, and parts are implemented in LLVM. And this split is a little bit tricky. And I know I'm really out of time, but just a little small example. Simple function has an int, has a struct that has a float, has a struct with 2 ints, a struct with 2 floats, a struct with 4 longs and an int. And you can see here, that's sort of the stack layout, that's still the old ABI. So the first 6 fields are really the fixed fields in the frame, which the ABI just specifies. And then basically this is this area that I mentioned where we could store the parameters if we wanted to construct a VA list. So that's the space that is left there for these parameters. And then just this very last one here is really actually passed on the stack, right? So if you look at the code that GCC generates, it's pretty much straightforward. It loads all the stuff up, and it stores this one last value on the stack, and then does the branch. So far, so good. If you look at what LLVM does, is first of all, we have Clang that generates LLVM IR. And if you look at this stuff here, you see that actually it has part of the ABI properties. It has already sort of represented in the IR. So for example, the fact that we have a struct that contains a single float, but we want to pass it as if it were just a float, has been done by Clang. So Clang has loaded the struct into a float and just passes here a float. But for the other stuff, it pretends, even though those structs are also passed in registers, it pretends they are passed by value. And then the LLVM backend goes and says, well, but the ABI says I don't really pass by value because I put it on the stack. But the effect is that you get code like this, which sort of puts it on the stack even though it wouldn't need to be on the stack, and then it loads into registers afterwards anyway. Which is not only inefficient, but it makes a problem with the new ABI because we don't have those fields on the stack. So we can't just put them on the stack because the space isn't there, right? So, and I'm coming to the end. This is the problem I'm struggling with right now is sort of, we basically have to define a second ABI on the LLVM IR. And we have to define it in a way that both the Clang implementation and the LLVM implementation makes sense and you don't have to duplicate too much of the implementation on both of the sides of the divide. And of course, we have to do it, we want to do it to get rid of this inefficient code we just saw, and we have to do it because now we don't have that space available. So it really has to be solved now. So if anybody, maybe anybody has some hints and tips, maybe I would appreciate if you could talk to me later. But right now, I'm pretty much out of time. Leave the summary up. And if we have time for 1 or 2 questions, maybe, go ahead.
Okay, so are there any questions?
Thanks. In the new ABI, do you still have the mandated frame pointer setup code that the old ABI has? You have to set up so you can do...
well, there's the backchain, which is still mandated. I mean. Yeah. We don't mandate a frame pointer, but you do mandate the backchain.
Yes, that's what I meant already.
Yeah. We debated that, but there was a lot of pushback because there are a lot of tools that really rely on that backchain being there, and so we decided to keep it.
Okay, thank you.
One last quick question. Oh, okay.
Why not RRP relative instructions since we only support Power 8 anyway?
Say again?
Why not use like x86, 64 user instruction pointer relative addressing?
Well, because Power doesn't have it.
Since it's Power 8 only, why not?
Power 8 doesn't have it either. It's this is an interesting discussion with the hardware folks, back and forth. Hardware folks say, oh, that's complicated and expensive. Software folks say, but it would be nice. So far, we don't have it. Maybe in the future, who knows, but right now, we don't have it.
So thanks a lot for your presentation.